is connecting. Take it away. Thank you, Sonia.
Thank you very much, Carmen, for the nice introduction. Hello, everyone. I'm very happy to be part of this amazing event. So today I will most likely talk about link in the thickened torus and particular type of link, which are called pseudo link, and how can we study the universal cover, which will lead to like some kind of doubly periodic entangled structure. But before that, of course, we are here to celebrate the birthday of Professor Lou Kaufman, and I've not been knowing him for a while, but I'm just very honored to be here today because, of course, like many of us, his work has been very inspiring. So one of the reasons that I'm studying periodic structure is actually because of my background, which is related to textile engineering and not much mathematics. And when I start to think about coming back to mathematics and get an interview to get a PhD, to become a PhD student, my advisor, who are actually a geometer and has nothing to do in knot theory, had this really nice book in her bookshelves. And I was like, I've never heard about knot theory before that. But of course, when I was thinking about textile, we are thinking about these yarns that are entangled. So I was thinking there must be some kind of relation. And it was like a huge inspiration to see this book. And when I started my PhD, the first paper that I've been really studying was like one of the proof of the tide conjecture using the bracket polynomial, because one of the challenge I was asked by a professor was to make a generalization of the tide conjecture for doubly periodic structure. So just to say that, of course, me being here is like a great honor because of all this work, which has been an inspiration. The first interactions that I had with Professor Kaufman was online through this really nice Oberwolfach seminar, which was organized also with Professor Colin Adams and Professor Sofia Lambropoulou. This was actually my first business trip as a mathematician ever. So coming from Japan, to Germany just after COVID. So that was quite a very wonderful event. And finally, just like 2 months ago, was the first time I had the chance to meet Professor Kaufman in person in Hiroshima, Japan, for this really great winter school, which was about knot theory and application in material. So here's exactly what I was saying. So coming from this background, which is a little bit far from mathematics at the origin, but which has closer connection, is all this thinking about this entangled type of structure we can find in many materials and systems. And it has been quite interesting to notice that a lot of the property, the physical or mechanical property of these materials are actually not a direct consequence of like the material or the chemical reactions that you will find, but most likely from the underlying topology or geometries that you will get. So for a simple example, if you think about this kind of structures that may represent a textile you can find in your clothes, just by changing the over and under crossing in this kind of structure will give you from the exact same material, say you made it with silk type of fiber, you will change the mechanical properties such as the rigidity, elasticity, and way more complicated physical properties. So thinking about this relation structure function, there is, of course, a huge interest and demand outside of mathematics, thinking also about chemistry and polymer science and so on, of having a good mathematical model of this structure. And it appears that knot theory is quite interesting to do that. So the relation is quite simple. If we think that we can model this structure having a doubly periodic tangles that I would call, you can see this object just as being some kind of universal cover of classical link in the thickened torus. You have also, of course, the diagrammatic version of this, which allow us to play and use the tool of classical link in the thickened torus. But we will see later that it is a little bit more tricky in the sense that when we go to the doubly periodic structure, there is a bit more thing to take in consideration. Hopefully, I will have the time to go through that. So as of today, we will not study a classical link, but we will study what we call pseudo-link. And I will tell you a bit what it is, started from the theory of pseudo-link in the thickened torus, and then see how we can go, if we have time, to the doubly periodic structure. So let's start a bit with some definitions. So here we are coming, it's like a very recent theory. We are talking about theory that is less than 15 years ago. And the motivation and all the setting came from Hanaki, actually, who was studying like structures that was observed, such as DNA type of structure, which was observed in a microscope. And it appeared that we know that we are talking about entangled curve with over and under information, but it appears that in some kind of experiment, this over or under information were not visible, like they could not catch this information. So you know that the information exists, but you don't know the over and under crossing information. And so the idea was, how can we make a theory that will work to model this type of structure? And this is where the theory of planar pseudo knot and link was stated, which is a diagrammatic theory from the beginning. And here we are just extended the definition to have a pseudo knot or link in the diagram in the surface of the torus. So this crossing, which we don't know the information, we will call them pre-crossing. And here we want to highlight that the main difference, of course, between knot diagram in the plane and in the torus will be that we will get two types of curve component, either nulomotopic and essential. And I will point that here. I want to point that here because this will be a consideration we will use later on. So we have obviously some kind of equivalence relation, diagrammatical on the diagrammatic level, which use an extended set of a Riemann-Master move. So here we have the classical R1, R2, R3. R0 will represent a planar or surface isotopy, depending on the surface we are. Here, obviously, in the torus. And we have three additional moves. PR1, PR2, PR3 here that give us also equivalence move when in the case that we are playing with this pre-crossing. So an equivalence class of toroidal pseudo-link diagram would be called just toroidal pseudo-link. Okay, so here, of course, we are also celebrating Luca Hoffmann's birthday, so it makes sense, since we will talk about the bracket polynomial later on, to have an extension of the definition of regular isotopy. So defining regular isotopy in the context of pseudo link here in the torus will be just to consider all the move except R1 and PR1. So if we have invariant of regular isotopy, it means that we will have, of course, invariance under the move R2, R3, PR2, PR3, and surface isotopy R0. So that will be a notion that we will use a bit later. As we said, we were talking about a diagrammatic theory, so we might be curious about the 3D object that can be defined as a lift of such a toroidal pseudo-link diagram. And here, the main challenge was to consider that, obviously, as we know in the case of classical link, we can consider the crossing as being like arc going in the north and south pole of a small 3 ball. But we had this concern about how what would be the embedded version of this pre-crossing, which are like most likely being seen as some kind of rigid vertex in a disk. And in that situation, we suggested to embed like the rigid disk together with this rigid vertex, so that we can define what we call the pseudo link in the thickened torus. And for a pictorial visualization, in the same way that we can define planar pseudo diagram as what we will call here a spatial knot or link in S3 or R3. We can also consider our pseudo link diagram in the torus and lift it in the thickened torus using the points that we have mentioned before. So here, the idea of having this 3D version, of course, is not only to have an extended version of the Reidemeister theorem, because we can indeed discuss isotopy of this pseudo-link in the thickened torus in terms of Reidemeister move and pseudo-Reidemeister move on the level of the diagram, as we have seen before. But we will see that there is another interesting point of having not only the diagrammatic theory, but also the corresponding three-dimensional link. And one of the reasons is that we will make use of what is called the theory of mixed link. And this theory of mixed link will be actually very important when we will talk about the doubly periodic structure, because we will also discuss the equivalence of the doubly periodic structure, and we will see that the theory of mixed link will help us to have a complete set of move to describe this equivalence on the diagrammatic level. So what is the theory of mixed link? So this was actually studied by Sofia Lambropoulou and Lulk together almost 30 years ago. And the main point here was to try to have to be able to study link in oriented, compact and connected three manifold, and to describe these links as some kind of mixed link in S3, like to reduce eventually the complexity of the study. So here, basically, for the particular case of link in the thickened torus, so here we see that it was needed to have the three manifold, like the link in the three manifold well defined. We will basically translate the notion of equivalence of this pseudo link in the thickened torus as some kind of mixed link, this time which are living in S3 or eventually R3. So here, this is how we define the H mixed pseudo link. So we will consider that the relation between the Hopf link and the thickened torus as being considering it as a link complement. And we will basically define a link in the thickened torus or a pseudo link in the thickened torus as being a link or pseudo link in S3, to which we will add two fixed components. So here, this will be a fixed Hopf link, and such that we preserve, of course, all the original crossing and pre-crossing from the original link that we will call the moving part, and such that the crossing between the fixed part and the moving part will not affect the equivalence relation, as we will see in the next slide. So here the figure is a little bit bigger, and here, so yeah, we already defined the relation between Hopf links and thickened torus. And the second point I'd like to highlight here is that we will be able also to consider the relation between the two components of the fixed Hopf link as being a meridian and the longitude of the torus on the diagrammatic level. And we will see that it will be quite useful later on when we will discuss the periodic structure. Okay, so I will go a little bit fast to not lose so much time here, but basically, as we said, we are able to translate the equivalence relation of pseudolink in the thickened torus on the level of H mixed pseudolink in S3. And going through by defining the diagram of H mixed pseudo link, which is defined quite basically, as we say, preserving the crossing and the pre-crossing through a projection from F3 to the plane, as we use it like naturally in the definition of not the link diagram. We're able to define this this mixed diagram. And of course, this leads also to some kind of generalized Reidemeister theorem when we do not only take into consideration the classical and the pseudo-Reidemeister move that we have seen before, but we need to add what we call here this mixed Reidemeister move, which will study how a fixed trend or a classical or a pseudo crossing behave when when we have isotopy with the fixed component of the Hopf link. So basically, we will say that we have equivalence when we pull an arc through a fixed trans or a crossing or a pre-crossing. Okay, so now what we are saying here is that we can somehow more or less, I guess it depends on the point of view, but reduce the complexity of the study of equivalence of this toroidal pseudo-link on the level of mixed link in S3. So one of the things we can do with all the tools that we have seen before is that we were talking about link or link diagram which have missing crossing information, but as we are saying, this crossing information is supposed to exist. So we want to have a connection between this pseudo diagram and the potential real diagrams that are lying behind that. So we have this notion of resolution that will like kind of give us a bridge between these two objects. So when we talk about a resolution of a toroidal pseudo-link diagram, so here we say we stay on the diagrammatic level, we are saying that we will consider all possibility of, I mean, first at least a random possibility of having a positive or negative crossing at each pre-crossing. And once we consider all the possible combination, then we will obtain a set that we will call the toroidal resolution set. We can do the same with the mixed link we have seen before, but as we will not go into the detail of mixed link anymore, we will stay just with the toroidal pseudo-link diagram. So let's see a picture to get an idea. So if we consider, so here it is a representation of a pseudo-trefoil, which is actually this pseudo-trefoil diagram is in the torus. And we have two pre-crossing. So we will consider that each pre-crossing can have either over or under information, and we will consider both possibility. So we have either here or here the two different type of crossing, and then we do the same with the second pre-crossing. And we end up with a set here of real classical, let's say, link diagram in the torus. We can see eventually if there is some Reidemeister moves that can reduce eventually the number of crossing, and which leads us with this set of, so actually we have 3 times the same, so we have these two diagram. And so this is what we will call the resolution set of this pseudo trefoil diagram. So why this resolution set is interesting? So there is many things. So one point that I will not discuss today is that here we can see that, as we said, the diagram number 1 3 and 4 are actually the same. So we have it appear 3 times, while this a bit more classical like trefoil with 3 crossing appear only once. So there is a discussion here that can be interesting in terms of probability of appearance of a diagram in a set. So this notion exists and is called the weighted resolution set, but I will not talk about this now. And the other interesting point is that actually it can be proved that this set is an invariant of the pseudo diagram. And this implies that if we get classical invariant of classical link diagram in the torus or link in the thickened torus, then the set of invariant corresponding to all this diagram give us also an invariant of the corresponding pseudo link, which is quite interesting as a way to find invariant. So this is what is stated here, is that we can have this kind of invariant. So the set itself is an invariant, and any set consisting of the invariant of each diagram, classical diagram, also define an invariant for this toroidal pseudo link. And of course, as promised, a small discussion about the bracket polynomials that can be defined. So of course, one way, as we have said before, we can say that the bracket polynomial here of these two classical link diagram, so the set with the bracket polynomial of the number 1 and the number 2, so this set of 2 polynomial will form an invariant of this toroidal pseudo link. But there is another way, which is to define the bracket polynomial directly on the pseudo diagram, which is what we are interested here. Okay, so let's talk a bit about the bracket polynomial. So in the case of pseudo link, so first planar pseudo link diagram. So Heather-Dye define two variable pseudo bracket polynomial, which is a direct extension of the classical Kaufman bracket polynomials that we know very well. So here we will find the classical skein relation, the relation when we take out the unknot with the variable d that is expressed in terms of a, the variable a, and finally the normalization for the unknot. And when we are talking about this time pre-crossing, so there is an additional skein relation that was defined by Heather-Dye, which is considering two additional variables and that allow a smoothing of the pre-crossing in a similar pattern that we have the smoothing for the classical crossing. So Heather-Dye had defined a relation between these two new variables, v and h. But here, because we want to keep the notion of regular isotopy and that this relation between v and h was done by Heather-Dye using the invariance of the move PR1, which we don't want to have now in the context of regular isotopy, we decided to keep these two variables as it is. And so this is the relation that defines a bracket type polynomial for the case of planar pseudo bracket polynomial. So for the planar case, we have our relation. But what happened, obviously, and of course, this was already considered even in the case of classical diagram without pre-crossing, is that obviously when if here we take one of the most basic type of diagram in the torus and that we apply the new skein relation for the pre-crossing, we observe that the state diagram contain essential type of curve, which is why I pointed out this at the beginning of the talk, meaning that here we don't have a normalization, we don't have a relation that allow us to normalize and to give a value of the polynomial when we only have essential component. So here, in the case of the classical link without precrossing, so there have been different way of doing the normalization, counting state diagram when we have only essential type of component. We choose a different way. So here we suggest new variable. So if you let me go back to this slide, one thing that we can say and one thing that is quite well known is that any essential closed curve or set of essential closed curves that will appear in the state diagram will be nothing else than a torus knot or torus link, which means that we can characterize this type of PQ torus knot by the number of times the curve will wind around the longitude and the meridian. And we choose to actually capture this winding of the curve through this normalization through variables that we will call SPQ. So SPQ, P and Q will be coprime numbers that will tell us for one curve that will be one torus knot, the winding around the longitude and the meridian. And if there is a set of such curve, if there is K such curve, it will give you a torus link with K component. So this is the additional normalizations that we have. And what we are saying here with this relation is that we can either at the end of a state diagram having one null homotopic component with the classical normalization equal to 1, or a set of essential curve. Because if we have both essential curve and null homotopic curve, we can use here the force relation to take out the unknot using the variable d. So it gives us a polynomial that is quite well defined. Here, eventually, we can say that maybe with this SPQ new variable, since we consider every possibility of torus knot, we have infinitely many variables, which can be a bit hard sometimes to consider. So we suggested a reduced version where this time this SPQ will be replaced by x at the power p and a y at the power q, when p and q still represent the torus knot and the winding of the component in the state diagram. And so we are reducing the polynomial not into an infinite variable polynomial, but only to 5 variables, which can be quite interesting. So it can be proved that it is invariant under regular isotopy, and analogous type of bracket polynomial, so the infinite variable and the reduced one can be also defined on the level of mixed link. And of course, it is possible using exactly the same type of technique as in the classical case, or for Pier 1 as Ezerdite did, defining a right and having a normalized version, such as a Jones type polynomial, which is an invariant of ambient isotopy. So here is an example of computation, both with the infinite variable and the reduced variable, which is marked by a small r. And here we use this example because it is quite interesting that to capture that just by changing the orientation of a single component. So here you can see that this component is oriented from left to right, and here we have the opposite orientation. And the skein relation for pseudolink, which are orientation sensitive, will just show that the change of orientation will give us a different type of polynomial. So here it will just be marked by the +1 or -1 of the state diagram, because here we will observe eventually, so depending on on the convention. So I will characterize this curve as being a 1-1 torus knot, and this one will be a -1-1. So here we have the opposite. So it is well captured by this polynomial. So, okay, I guess I have 10 minutes left. So I want to tell you a little bit about how we can relate all this theory of toroidal pseudo-link to the doubly periodic structure. And as we mentioned, so actually, even if the relation seems quite obvious between the link or the pseudo-link in the thickened torus and the corresponding doubly periodic structure, we will see there is a bit more point to take into consideration when we define equivalence. So let's talk a bit about the definition. So I think the pictures we have seen before like speak for itself. If we want to be a little bit more precise, as in the same way that we define the theory of toroidal pseudolink first as a diagrammatic theory, we will also start first with a doubly periodic diagram. So here the thing is just to make a relation between the longitude and the meridian of the torus with a basis of the Euclidean plane, and to use a covering map to link both of them. And so the picture we have seen before here marks this. So we choose a longitude meridian pair, and we get using the covering map, we get the doubly periodic structure. So this is formalized this way. And so we can define the pseudo doubly periodic diagram. So I will use DP from now for doubly periodic. We will call the link diagram a motif from now. So we will talk about pseudo motif diagram. And we will have sometimes some interest of seeing this motif on the level of the flat torus. So we will call about flat pseudo motif when we cut the torus along the longitude meridian pair, which is related to the covering map, right? So we can see that we are always considering a motif together with its longitude meridian pair. Okay, so here, first, very interesting point is that we can see whenever we have pre-crossing or actually just classical crossing, it is obvious that if you take any finite cover of your given motif, your given link diagram in the torus, you will end up with another motif of the same doubly periodic structure. But in the case of pre-crossing, here we have a tricky point. If you are given a motif, a pseudo motif with pre-crossing, the distinction with the classical crossing is that we want to give some kind of label of the pre-crossing such that the information of the pre-crossing, which is supposed to be either over or under on principle, will be kept when we go to any finite cover. So this is what we will call homologous pre-crossing. This notion of homologous pre-crossing is very important when we want to discuss later the interest of finding the kind of minimal motif with a minimal number of crossing eventually that will correspond to the same doubly periodic structure. So it means that if we don't have homologous pre-crossing, we cannot quotient the motif into a smaller one at some point. So this is an important notion. Then another point is, as we said, in the same way that we were talking about lifting the diagram into a 3D object, here we do exactly the same. We will consider that since our pseudo link diagram in the torus can be lifted into a link in the pseudo link in the thickened torus, so we can define the notion of pseudo DP tangle, which will be this time the universal cover of the thickened torus, and that will give us a pseudo doubly periodic tangle being embedded in the thickened plane, right? And so we will have the motif, which is just the link in the thickened torus. Okay, so we have seen before that first a tricky point is this notion of having different type of motifs that will correspond to the same doubly periodic structure. We discussed about finite cover and quotient, but that's not only the things. Another possibility is just to notice that when you have a doubly periodic structure and you have given a periodic lattice, you can make a change of basis using the same point lattice to get other type of somehow unit cell, so of flat motifs that will correspond to the same doubly periodic structure. And what is very interesting to see here is that when we consider here UV and U prime V prime, so here you might eventually be confused that I'm saying that this U prime V prime will correspond to this flat motif. And this is just done by considering that an intermediate step, which is the identification of the two opposite sides, and then recutting along a more standard longitude and meridian pair. So here we are seeing basically a first hint of an equivalence relation, which is when we are taking two different bases, of the same doubly periodic structure, we might end up with link diagram or link, which are absolutely not isotopic in the usual sense. So, small summary in the figure, we have infinitely many possibility of choosing infinitely many link diagram or pseudo link diagram in the torus that are not necessarily isotopic, but that will lift to the same doubly periodic structure. And obviously we are looking for equivalence relation between them to define the notion of equivalence. So to go quickly, because I think I don't have much time. So we can describe the isotopy considering we will preserve every doubly periodic property. And this was something initiated actually by Grizanov, also working in textile knot theory more than 10 years ago. And one of the first things, one of the easiest moves that we can consider are, of course, the classical Reidemeister move, pseudo-Reidemeister move, surface isotopies that we have seen in the theory of toroidal pseudo-link. And we will also consider that we can, in the same diagram in the torus, we can change the choice of longitude meridian that will give us some kind of shift or translation on the level of the doubly periodic structure. So this is something that we take in consideration into what we call the local equivalence. Then, using the notion of mixed link that we have seen before, we were able also to define all the detail of surface isotopy, at least on the level also of the flat torus, since we are talking about curves that are passing or crossing and pre-crossing that are passing through the longitude and the meridian. So all the moves that we have seen before on the theory of mixed link apply here and give us a complete set of moves that describe the equivalence, local equivalence at least. Then we need to go into a bit more global equivalence. And what was done by Grizanov and his team when they were studying textile with knot theories was to consider that indeed the change of basis that you can consider in a point lattice can be translated on the level of the motif as a den twist of the torus. So all of these den twist means can be interpreted as a change of basis for the fixed pseudo DP tangle, and they can also be considered as a shearing, so as a doubly periodic isotopy, global isotopy of the structure, which is quite interesting. And finally, what I've called scale equivalence, so that was one of the first things that I was doing when I started my PhD, was, as I mentioned, giving this kind of equivalent relation when we have a covering map, a finite covering map that relate the two motifs. Okay, so we have this generalized type of Reidemeister theorem, and we can state that two doubly periodic like pseudo tangle can be equivalent if we can find two motifs like pseudo motif of them, which will be related by the different point we have seen, all the local equivalence, the then twist, and the scale equivalence. And of course, everything that we have seen before raised the question of finding this kind of minimal motif, which will be up to all this equivalent move, the type of motifs that will get, obviously, of course, the minimal number of crossing, but that will also not be a double cover, for example, or any finite cover of another motif. So these are all the tricky points to take into consideration. So I will go fast because we are out of time. So we have this resolution. So let's go directly to the picture to get the idea. We can resolve each pre-crossing as a positive or negative crossing to get the resolution set. And of course, if we go to a finite cover of this motif, each pre-crossing which are homologous will resolve exactly in the same way. So we end up with a set of two classical motifs for even though we have two pre-crossing because they are homologous. However, if they are not homologous, we will consider them different from the beginning, and we will resolve them one by one to get at the end a set of 4 elements for the resolution set of this toroidal pseudo DP toroidal this pseudo DP tangle. This can be proved to be invariant. And a very last slide, few slides to discuss what will be the bracket polynomial for the doubly periodic structure. So as we said, we can think that instead of studying, we cannot study the bracket polynomial of the infinite structure because we have an infinite number of crossing. So we will go on the level of the motif, so on the link in T2 cross I. We already have the relation as we have seen before. So we can say like, okay, we are happy, but we need to remember that if we want to define invariant for infinite doubly periodic structure, I could say more about that, but I don't have time. It's very important to find first this kind of minimal number of minimal pseudo motif to consider the local equivalence, and very important here to consider all the then twist. And this will be left as an open question for now, even though we have almost finished, and hopefully we will show that in a paper soon. As we can see that the state diagram will contain essential curve, and that a then twist will change the winding of this curve, so we don't have an invariant under then twist, and it is very important to make this stabilization of the then twist. Khrysanov already had one solution in his paper, and we choose a different direction, so we are looking forward to show you that in the future. So thank you very much, and all my best wishes for the birthday of Professor Kaufmann again. Thank you very much.
Thank you, Sonia.